Hi you guys, today I'm going to talk to you about the polarity of covalent compounds. So let's talk about what polar molecules are first. So what you will need today is, of course, your notes. You will need a pen, highlighter, and you will also need your electronegativity chart that we talked about earlier. And along with the electronegativity chart, of course, you will need a calculator to do the calculations. Okay? So let's get started. Okay, so let's talk about these, what polar molecules are. Okay, so the molecular shape causes one end of the molecule to have a slightly, I'm going to say one end of the molecule to have a slightly positive charge, and the other end of the molecule to have a slightly negative charge. This is called a dipole moment. Okay, and when the molecule has a dipole moment, then the molecule is considered to be polar. And that means that the molecule is unsymmetrical, and so the dipoles are found and they do not cancel one another out. Okay, so what exactly does that mean? Sounds like a lot, but what it's talking about is sometimes you have molecules that do not share electrons equally. And when you have molecules that do not share electrons equally, you will have these electrons will move to one part of an atom. So when they do, we call this partially positive and partially negative. The way that we say that something is partially positive is we make this symbol right here, this cursive looking sort of an S with a little squiggly line around it. So I'm going to move it up close. Okay, so right here. And we say that this is partly positive. Okay. And what this is saying is that this has less electrons. And that's why it is partly positive, because it has less electrons. Electrons, remember, are negatively charged. So when we have partly or partially negative, now we're saying that this part of the atom tends to have more electrons. And the reason why all of this is possible, and you want to write this down, all of this is possible, sorry, there you go, you should be able to see it now. All of this is possible because electrons are moving. Okay, so these electrons are never staying in one place. They're moving around. Sometimes instead of saying moving around, we say that they are actually delocalizing. Okay, they're delocalized right there. Okay, so let's talk about some examples of it. One thing that you do need to remember when we talk about these electrons is we're talking about that they have a lone pair on the central atom. So when you're trying to identify whether something is a polar molecule, you always want to look at the central atom. And if the central atom happens to have lone pairs, then most probably it's a polar molecule. Okay, because it has polar bonds. And keep in mind that polar bonds, the electrons are not being shared equally, and that's why one side is partially positive, and the other side is partially negative. Okay, because they are not being shared equally. And if they're not being shared equally, that means that the molecule itself is unsymmetrical. Okay, let me stop this and get a better picture for you guys. So if you want to write here on the side, unevenly sharing of electrons. Therefore, and I write my therefore like that, therefore it is unsymmetrical, meaning it's not going to be symmetrical at all. So this is what a polar molecule is. Okay, so here's an example that I have, two examples. And my first example is good old water, H2O. Okay, so if we look at water and we look at the types of bond that they have, we have water, oxygen, and hydrogen. Okay, so looking at your negativity chart, you have your negativity chart. You're looking at oxygen, which is 3.50, and hydrogen, which is 2.20. Okay, don't forget you are taking a negative, an absolute value of the two. One is 2.20. And of course you can put this in your calculator if you want. It does not matter. Or you can do the simple math yourself. Either way it works, really. So it comes out 1.3. Okay. 1.3, and if you recall from your notes when we talked about types of bonds, that this would actually turn out to be a polar covalent bond. Now that means that these electrons are being unevenly or unequally shared. They're moving to one side, these electrons. Therefore, it is going to be unsymmetrical and it's going to be polar. But we can actually see that in our picture. So if we actually draw the shape of water, and you know that the shape of water is bent, and according to the Lewis dot structure, there are two lone pairs, those lone pairs that are there. Well, keep in mind that those lone pairs, I'm going to write this down, they are partially negative because they're lone pairs, they have negative charge. And these hydrogens, well, these are positively charged because the electrons are actually moving towards the oxygen and the electrons there, right? So they're constantly moving around. So you have this pull of electrons. This oxygen is actually pulling the electrons toward it, okay? So this pull on both sides right here, it's like a tug of war. It's going to equal, since they're both hydrogen, the pull is about the same, so they're going to cancel one another completely. But realize that this oxygen has two pairs of lone pair electrons. And again, see if you guys can see it. So this oxygen has two lone pairs. So these lone pairs are also now pulling everything up towards it. So it's actually pulling up, and I'm just going to draw it here on the side that our dipole moment now is being pulled up. And so we have equal pulling from the hydrogens, but this oxygen right here is pulling a lot more. So therefore, it is unequal sharing of electrons that we have. It is unsymmetrical because even though the pull is the same on the sides of hydrogen, it's the oxygen that nothing else is counteracting or canceling the pull up. So it is unsymmetrical. So we say that is polar covalent. Okay. Second example that we have here is, again, lone pairs are nice. So you always want to try to, if a shape has lone pair electrons, chances are that it is polar, it's a polar molecule. So I'm going to go for ammonia and H3. And I've got ammonia that has nitrogen and hydrogen. And we're looking at our electronegativity chart in this case. Nitrogen is 307. Hydrogen is, you should be able to see it, 2.20. Okay, so if we start subtracting, writing this down, keep in mind, you guys, that this is all this is absolute value, that we are always dealing with. Electronegativity is the absolute value to 0, and so that is going to eventually equal 0.87. If you recall from your notes that this happens to be, it lands in that sweet zone, and it is polar covalent. But, you know, the math, we look at the math, but really it's the picture that says a lot more than the math. So if ever you're in doubt of what it is, draw your picture, and you should be able to answer the question of whether it is polar or not. So we've got our picture right here. Well, these two hydrogens, the electrons from these hydrogens, are being pulled equally. Okay, so they are being pulled towards the nitrogen, the lone pairs. So we're going to cancel these two guys out. Okay, and then we've got this hydrogen that the electrons for this hydrogen are also being pulled. Okay, but then guess what? We've got this extra pair of electrons. Well, this extra pair of electrons is doing even more pulling. So you've got, not only do you have the hydrogen where the electrons are being pulled, but this electron is even pulling even more. So yes, it does end up being a polar covalent compound. Okay? Okay. So now let's look at what nonpolar covalent means. Okay, so now let's talk about nonpolar molecules. Nonpolar molecules are actually the exact opposite of polar molecules. These molecules, on the other hand, are symmetrical molecular shapes that actually cancel out the dipole-dipole moment. Okay, so they actually cancel out. So what that means is that these molecules are, the electrons are shared evenly, and because these electrons are shared evenly, you have the molecule is now symmetrical. Okay, so it is symmetrical, which is why it is a nonpolar molecule. Okay, so let's see. Let's do some examples here. We've got an example of, so let's start with the first one. We've got CH4, okay, methane, and we've got carbon and hydrogen bonds. Okay, so we're going to use our electronegativity chart, and when you do, you're going to see that carbon is a 2.50 minus 2.20. Okay, so it is a 2.50 minus 2.20 right here, and when that happens, it comes out to be 0.30. And if you look at your electronegativity chart, which you're supposed to memorize, you will see that this is a nonpolar covalent molecule. But don't take the word of the math. Look at the picture also, which can say a lot more than the math can. So if we draw our molecule, we'll realize that this is actually a tetrahedral. So, and then, so you've got hydrogen, 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 hydrogen. Okay. Now when you look at this, you've got the hydrogen that's being pulled. Carbon happens to be more electronegative than hydrogen, so the electrons are all going to move towards carbon. So these two hydrogens cancel one another out, the pull of it. And then you've got this one. Well, the electrons are moving, and the electrons for this hydrogen are also moving, and these two now cancel each other out. Since they're canceling each other out, that means that the electrons are being equally shared in this particular molecule, and you can see that by them being symmetrical, where no force on any one particular side or element is being is stronger than the others. So in this case, this is a no dipole. Okay, there are no dipoles at all. Okay, let's do another one. Let's do carbon dioxide. So we'll do CO2 right here. And when we do, we look at carbon and oxygen, the electronegativity. We're going to look at the math first. And so according to our electronegativity chart, oxygen happens to be 3.50, carbon is 2.5. Okay, and again, you guys, this is absolute value, so that is not going to, we're not going to look at the positive, negative numbers. So when we do, this comes out to be 1.0, which means that it is a polar covalent molecule. But let's draw our picture and make sure, which is which says a lot more than the math right now. So we've got our carbon, that it's double bonded to the oxygen. And in this case, unlike the methane right here, notice over here that the most electronegative element between carbon and oxygen is clearly oxygen. Oxygen has those lone pairs that are pulling the electrons from carbon. Also, oxygen tends to have a greater electronegativity. So that says a lot. So when we draw the electrons, these electrons are going to move from the partially positive, which is carbon, to the partially negative. So they're going to move that way on both sides. Okay. So when they do, it is now an equal pull of electrons. They're being equally pulled. So it's an equal sharing of electrons, and so we say this is symmetrical. So this turns out to be the dipoles cancel, and we say that this is a non-polar molecule. Okay, non-polar molecule. Let's do one more as an example. SF6. So we're looking at sulfur and fluorine, the electronegativity of it. So what this is actually saying is that you've got your van der Waals forces are actually very much dependent on whether a molecule is polar or it is non-polar. Okay, so that's what they're saying. So you've got these van der Waals forces, and within the van der Waals forces, you have, you have strong van der Waals forces and you have weak van der Waals forces. And when we talk about hydrogen bonds, we are talking about the elements nitrogen, oxygen, and fluorine in particular. Okay, so the hydrogen will bond to nitrogen, oxygen, or fluorine. Enough. Okay, if you want to remember that. And then the dipole-dipole, keep in mind, dipole-dipole existed when a molecule was polar. That means that it is unsymmetrical. It is uneven pulling of those electrons. Okay. And then we have our weaker van der Waals forces, which are just the basic, typical London dispersion forces. Actually, these London dispersion forces are within all molecules, okay? So all molecules actually have London dispersion forces. But what we say for weak van der Waals is that the weak van der Waals don't have any other molecule, any other forces. They just have the London dispersion forces, okay? So that's what we're actually saying. So just to clarify, when we talk about strong van der Waals forces, we're talking about that both hydrogen bond and dipole-dipole is they're polar covalent compounds or molecules. But the dipole-dipole, remember, it is the unequal sharing, so it's unsymmetrical. The hydrogen bonding is also unsymmetrical because you're having a hydrogen bond that forms between nitrogen or oxygen or fluorine. So it forms that, and it is still unfair, unequal sharing of electrons, so it is still unsymmetrical molecules that you have. Okay, this right here where we talk about weak van der Waals forces, and the force that exists is really we say that it is the London dispersion force. What we're actually saying is that this is non-polar covalent forces that are here. And the reason why these the London dispersion forces, or LDFs, exist is because it's basically an attracting force that we have. So non-polar molecules exhibit only LDFs. That is the attracting force that is there. Okay, because these molecules lack a dipole moment, the process is known as polarization, okay, which allows for temporary dipoles to exist as the molecules approach one another. Okay, so polarization is a temporary fix, allowing the dipole moment to occur. So these molecules can at least get together, because when these electrons move from one side of the atom to the other, they're moving there because they're probably attracted to something else. And this phenomenon is more pronounced in larger molecules and more easily induced to become polar. So polarization is happening all the time in the molecules that we have. Okay. So let's draw a picture real quick. So 1, 2, 3. I guess if you want to draw 3 circles, you can. Okay. So the first circle that I'm going to put in is called the H bond. Okay. That is the strongest and strongest force that we have. It's very particular because it's requiring hydrogen to bond with nitrogen, oxygen, and or fluorine. Then after that, we have dipole-dipole moment. That is also the next strongest. Okay, and because these electrons are moving around, we do have LDFs that are also present, and that is along with van der Waals forces. So van der Waals forces. Okay, and then at the end we've got more of these polar molecules that are here. Your nonpolar molecules, the only force that really applies to nonpolar molecule is London dispersion forces, or LDFs. And these are basically van der Waals forces. Because the element are symmetrical. That means that they're equally sharing electrons, okay, where they don't have that partially positive and that partially negative areas in a molecule. Okay, and so polarization is having delocalization or delocalized delocalization. And that means that they're, partially positive and there are partially negative areas, but that is very temporary. Okay, that's enough to allow a reaction to occur that's happening between them. Okay, so let's talk about solubility. Solubility, you guys, especially in water, depends on the polarity of the molecule. Molecules that are more polar tend to be more attracted or soluble in water. Okay, and remember that when dissolved, the molecules themselves do not break apart. So when these molecules start dissolving, they don't necessarily break up in the water at all. Rather, it is they form intermolecular forces between other molecules that may be broken up. Okay, so if we are talking about our IMFs, that's intermolecular forces. A good example of H bond would be something like a bond between hydrogen and fluorine. Okay, and this would of course be polar that we have because all H bonds are polar molecules. Dipole-dipole, an example of dipole-dipole could be as simple as oxygen dichloride. And this, of course, you guys, you have oxygen in the middle, chlorine on both sides. Okay, and of course this oxygen also has electrons that are pulling on it. Because these electrons are pulling on it, you've got oxygen is more electronegative, so you've got the chlorine electrons are moving, and then you've got oxygen that is pulling electrons. So this would actually be uneven pulling. That's why it's a dipole-dipole. So it would be polar molecule. Okay, it'd be a polar covalent molecule. And then last but not least, an example of non-polar molecule would be PCl5. Very simple. So if we draw a shape, we've got phosphorus, chlorine on both sides, and on one side you've got chlorine. On the other side, you also have chlorine. But then this chlorine is being pulled. This chlorine is being pulled on the opposite side. So if we look at the dipole moment, let's see, according to our electronegativity chart, phosphorus is a 2.06, and then we have chlorine, which is 2.83. So chlorine is more electronegative. It's pulling the electrons from phosphorus on both sides. Well, these two sides cancel one another. And then you've got these electrons that are being pulled to this chlorine as well as this. But then they're being pulled collectively towards the other side. So what's happening is that even though you've got an electron, this chlorine right here is pulling the electrons, you've got these two chlorine that are balancing the pull of this other electron right here. So they're actually balancing it. So these two actually are the pull of this one electron that is splitting off. So these two are splitting off the pull, okay? So they actually cancel one another out. So in this case, this would be a non-polar covalent bond because it is being equally pulled. It is symmetrical. Okay, and of course the most famous one that we have is H2O, which is of course full of H bonds. The bond is between hydrogen and oxygen that we have. Okay, so that is definitely your H bond. But this concludes our lecture over polarity of covalent compounds and talking about IMFs, which are intermolecular forces. Remember that you have your intermolecular forces, or the types of intermolecular forces that you have. So everything is really a van der Waals force, and the van der Waals force the background force that we have is really called the dispersion force for everything. Stronger van der Waals forces are polar, and an example of polar bond would be hydrogen bonds or dipole-dipole, which is a polar covalent bond. Your weaker van der Waals forces would be just, there really isn't any other force other than the London dispersion force that exists. So this would be our nonpolar covalent. So these are our different types of IMFs or intermolecular forces. Thank you, and I'll see you guys later. Bye.